The third law of Newtonian dynamics, action-reaction, it is a fundamental physical principle that contains the concepts of conservation of energy, causality, and localized interactions. Also, physics has always one answer. It is consistent. From the same action, you always have the same reaction, and the reaction is proportional to the action. It must also be remembered that energy cannot appear or disappear. It can only move and transform. If I have a system here and have to go here, it can only move and cannot do it in any other way because energy cannot be destroyed or created, and teleport is a human bias without physical logic. Even if we can make the system disappear here, which we can't, why something should appear here? The system doesn't exist anymore, and the distance matters as much as the space the system occupies. And this is true at every scale. Quantum physics point particle is something it created, and it is its own problem. And no matter what is inferred, there is no experiment that violates localization of energy and space-time relativity. When we are dealing with structured and complex systems, there are many cases where instead of evaluating the individuals, we can look at the overall behavior, the emergent properties. And a typical example is temperature. The whole can be defined chaotic, and it is not possible to keep track of individuals, but each component has its own completely defined values, and it's possible to identify a statistical group behavior. Even within chaos, the physical principles remain, so each component will act or react following this. There is always a reason, and there is no spooky action. The statistical behavior can also be applied to systems small and fast, as is in example the electron. Even here we are looking at deterministic systems that follow the same physical laws. The wave floats in this space-time, and the statistic is here related to where we can more often find the electron by collision. The electron also has an electric field, so we can interact with the system even without a direct hit on the particle component. Now, randomness is a different concept. Randomness is the only that really has the unpredictable factor, and it is only identifiable in some actions of life forms. Seeing a leaf blown by the wind is not surprising, but if the leaf moves because it is intentionally collected, the action-reaction concept falls apart. There is no reason for this to happen, and the event is unphysical, since it is our choice to pick up the leaf. This marks the difference from chaos, because the will of a life form can act against physics. But this doesn't mean that randomness can break or violate physics. It means that there is no direct physical explanation for the event. The same is also true in animals. There is no physical reason why a prey at the sight of a predator runs away. Meaning, if it were up to physics alone, each life form shouldn't move from where it is. It shouldn't even stand up. And you see it when someone faints. Yet the prey can react just at the sight of the predator, and their reactions are unpredictable. So, from the same action, we can have many different reactions, and we don't have univocal logic. Random doesn't mean 100% unpredictable. Archetypes, instincts, habits, they all influence the actions. So even randomness can be statistical with some degree of predictability. And while the actions of life form are not always random is always from life forms, because physics cannot be random. There are now cases a little tricky, because we have a real mix of the two. Whether it's the toss of dice or coins, and ignoring the small differences, there is no physical reason why the result should follow any statistical trend. It is we humans who give different values to different phases. In physics, all sides are equal. Randomness of the results depend on our thoughts because the life form is the randomness factor. And since randomness doesn't require consistency, there is no reason for the results to be equally distributed over all phases. When dice or coins leave our hand, the behavior becomes 100% deterministic in a chaotic way, but the influence of our randomness cannot disappear. And overall, the statistics is about something that doesn't affect or is related to the result itself. This is also useful to remark that no computer can simulate true randomness, including dice and coin toss, because randomness comes from the actions we perform through will. To summarize, both chaos and randomness can be statistics, but the two concepts are not interchangeable and must remain separate. On one side, there are physical actions of chaos, having consistency beneath complexity, and causality. On the other, there is unphysical randomness with no consistency and causality. In chaos, there is always a reason. You can average or approximate, and in theory, you can always make predictions. While in randomness, your statistics and predictions can be contradicted at any time. You don't know what you don't have a real control or knowledge about. While chaos is our difficulty in managing a complex problem. It is not an intrinsic feature of the interacting systems. They keep acting with 100% coherence. Problem now is that while classical physics is related to chaos, quantum physics uses randomness, making the theory dramatically wrong in its fundament. Quantum physics uses randomness to represent something that is chaos. And it is hard to spot the mistake since quantum physics is not observable and both chaos and randomness flow into statistics. So how can quantum physics work anyway? Say these are the possible outcome for quantum physics, and this can be doubted since with the wave function we have infinite probabilities. Inside these we have the possible outcomes from deterministic theories, and here we have what we experiment or observe. We can see how quantum physics is counterfeiting determinism. Results from the randomness never exceed the deterministic chaos, while quantum effects cannot be seen and don't make any difference because they are here. Quantum theories encompasses a wider range of theoretical outcomes, but all experimental results and observations are always inscribed within classical physics. So we can have statistics both from quantum mechanics and classical physics, but they come from very different concepts with very different meanings. And we can't really compare the rules of chaos with those of randomness. We can talk about conservation of energy, relativity, or more in general about physical rules, because randomness is not physics. A statistical behavior doesn't imply that quantum is necessary, and unlike quantum physics, determinism acknowledges the ignorance of the humans, but reject the ignorance of the self. Each system knows itself and is always fully defined in the space-time continuity. A couple of side notes. Standard deviation doesn't show that quantum physics can be proved wrong or it follows scientific method. Standard deviation does not question the theory. Quantum physics is assumed correct, and we are just looking at some divergence between arbitrary statistical models. And there is no care about reality. Randomness in quantum physics means things happen at a fundamental level with no reason or explanation. Quantum fluctuations are energy that appears from nowhere and in the same fashion later disappear. There is no why or how. And as always, we can't observe them, and this violates energy conservation. Even background noise has a source and follow physical laws. And not understood doesn't imply random. An example of conservation of energy on statistical base is the nucleon model. According to quantum mechanics, inside each proton there are valence quarks, gluons, and C quarks. Protons in ground state have a specific amount of energy that comes from everything inside. Now, the many C quarks are not connected, related, or interacting. They are pure randomness without underlying logic. Yet, for one that goes out of existence, another C quarks with exactly the same amount of energy comes out somewhere else. And this keeps going, having the overall energy conserved by average. The energy is conserved by statistics of randomness, and this is a logical contradiction. In quantum mechanics, we can often have independent systems that violate physics, respecting it only as a whole. And even if it's not observable, this behavior remains unphysical.